Welcome again to the world of wholesale electricity markets. I'm Keegan Trujillo Green. This presentation is a companion series to my articles on how electricity markets work. In the last video, we got some background to wholesale electricity markets and the grid, and in this video, we'll learn about the supply and demand of electricity. To understand the wholesale electricity market, one's got to understand the economic principles of supply and demand. To do so, let's start with a market example that seems unrelated to the electricity market, but is more familiar and intuitive. So imagine a neighborhood of cafes, all of which serve espresso. What a great place to live. The baristas will make as many espresso shots as customers buy. More specifically, at any given time, the rate at which baristas supply espresso shots, such as in shots per hour, is always equal to the rate at which customers are demanding them. For reasons that will become apparent later, we'll assume for the sake of example that all of these cafes are serving identical espresso and to offer an identical overall experience to customers. Because the cafe's offerings are the same, and they're conveniently located within the same neighborhood, the only thing that would set them apart in the eyes of customers is their prices. But if a cafe tries to undercut its neighbors, the other cafes will follow suit if the lower price is sustainable, in order to stay competitive. And if a cafe raises its price to increase its profit margin, others will be able to do the same. So for a given time, place, and offering, there is one stable price. Different cafes may have different operating costs. Perhaps one cafe has a more expensive supplier of espresso beans, but they tend to charge the same price per espresso shot and pocket the difference. Customers' demand for espresso shots is based on how much the cafes charge for each one. There will obviously be fewer customers if the cafes charge more, and vice versa. So the rate at which customers buy espresso is a function of the price per espresso shot. This function is called the demand curve. It models buyer behavior in aggregate and is generally monotonically decreasing. The demand curve changes with time. For example, demand for espresso is greatest in the morning. Now we'll look at the supply side. If the cafes have to make more espresso, they'll have to purchase more espresso beans. They'll have to call upon additional baristas to help, or have to pay each barista more per hour, and that factors into the cost per shot. The cafe's cost per espresso shot is reflected in the price they charge for each one. However, the cafe's price per shot is not constant. If the cafes are overwhelmed with customers, they may charge more for each espresso shot to take advantage of the situation and make more profit per shot. The cafes may have to augment the barista's hourly wages with bonus pay to keep them happy. To meet the demand, the cafes may have to bust out their older, less efficient espresso machines from their back rooms that use more espresso beans per shot. Now, on the other hand, if the cafes are having a slow day, they may reduce their price and sacrifice some profit per espresso shot to make the most of the low demand. This is called dynamic pricing. The price is a function of the rate at which espresso shots are being sold. This price is known as the marginal cost of supplying an additional espresso shot per hour. The price function is called the supply curve. It models seller behavior in aggregate, and it's generally monotonically increasing. Note here that a given cafe is willing to sell espresso at or above a certain price, and a given customer is always willing to buy at or below a certain price. These principles are true not just for a neighborhood of cafes, but for any capitalist market. These basic tenets of economics are the principles of supply and demand. They apply whenever a quantity Q of a particular good is exchanged at a price P. Q is measured in goods per hour, and P gets measured in dollars or any other currency per good. The allocation of buyers to sellers, or customers to cafes, is a process called clearing the market. This determines the quantity of goods that gets exchanged in the market, Q star, and at what price, which we denote P star. This price is known as the market price or market clearing price. Sellers who charge a low price are able to produce at a low cost and don't price gouge. A capitalist market rewards such sellers and gives them priority over other, less efficient ones. At the same time, a capitalist market rewards buyers who are willing to pay a high price, giving them priority over other buyers who don't value the product as much. It follows that we can model the market clearing process by allocating an increasing quantity of goods to the buyers and sellers, starting with the buyers who are willing to pay the most and the sellers who are willing to charge the least, until the buying price equals the selling price. We can represent this model graphically, or mathematically, by plotting the supply and demand curve as shown. The market clearing price P star and quantity Q star are dictated by the point where the two curves intersect. The area under the supply curve until a quantity Q represents the cost, denoted C, of producing that quantity. And the area under the demand curve until a quantity Q represents the cumulative value delivered to buyers by that quantity, known in economics as utility, or U. And yes, this does get confusing when we're also talking about utility companies. Subject to the constraint that the quantity sold must be the same as the quantity bought, Q star simultaneously maximizes buyer utility and minimizes seller cost. The difference, U minus C, is known in economics as surplus or welfare, denoted W. And in clearing the market, it's welfare that's maximized. Welfare can be split into two parts: producer surplus and consumer surplus. Producer surplus is the area above the supply curve but below P star, representing the profit earned by selling above the cost of production. And consumer surplus is the area below the demand curve but above P star, and that represents the extra value delivered to customers beyond what they paid for. Now, obviously there's no regulatory body that allocates customers to cafes. There is no economist planted in town trying to find the intersection between the supply and demand curves. Your friendly espresso market clears itself. Cafes try to charge the highest price that the optimal number of customers are willing to pay, and customers naturally seek out the lowest price that the cafes are willing to charge, and the two sides generally meet somewhere in the middle. The principles of supply and demand are so universal that they apply to the electrical grid when operated as an electricity market. In this case, the good is not espresso shots, but megawatt hours of electricity. So energy for machines rather than for humans. The unit of measurement is not espresso shots per hour, but megawatt hours per hour. So just megawatts. In a wholesale electricity market, the rate at which electricity is supplied, which is the production or generation, is always equal to the rate at which it is demanded, the consumption or load. In the cafe analogy, generators are espresso machines, and loads, like your local utility company, are customers. Everything that we've talked about so far in terms of cafes and capitalist markets in general applies to the wholesale electricity market. Even taking out your less efficient espresso machines when demand for espresso is high is analogous to firing up less efficient gas-fired plants when electricity demand is high. Now, we assumed before that all cafes served identical espresso. In other words, we assume that espresso is a commodity, a good that varies little between sellers and that buyers are not picky about. Obviously, this isn't true about espresso in the real world. Examples of commodities include wheat, crude oil, and electricity. Indeed, all electrons are created equal. Electricity may be produced from a variety of energy sources, nuclear, hydro, and so on, and travel varying distances to get to your home, but there's no differentiating between a nuclear generated electron and a hydro generated electron. People care about the origin and locality of their food more than that of their electricity. And yes, some people care about the environmental sustainability of their electricity, I among them, but we can't choose between sustainable and unsustainable electrons. We can only choose to consume electricity at times of day when there is a higher proportion of sustainable electrons in the mix. But at a given time, all electrons are equal. So we've talked about the market clearing process. The wholesale electricity market must be cleared like any other, but unlike a neighborhood espresso market, it cannot feasibly clear itself. There are two reasons for this. First of all, there's no buffer between production and consumption. Let's look at this through the lens of the cafe analogy. If cafes are busy, customers can feasibly wait for up to several minutes between placing their orders and receiving their espresso. Alternately, the cafes can prepare extra espresso shots while morning demand is still ramping up to reduce customer wait times. But this does not work in the electricity market. When you turn on your kettle, for example, you don't have to wait even a second for power. You just take. The grid cannot ramp up in advance of everyone turning on their kettles in the morning because traditionally there's no way to store that extra power. And the second reason for which the electricity market can't clear itself is that resources are pooled. So when you want espresso, you go to one cafe and you talk to one barista who fulfills your order. But when you want to turn on your electric kettle at home, you don't call up a generator and ask them to ramp up by a couple kilowatts. There's that disconnect between the demand, you, or rather your utility company, and the supply, the generators. So the wholesale electricity market must be administered by a regulatory body, the system operator that monitors the demand and tells each generator how much to supply, such that the total supply exactly equals the demand at all times. It's worth it to have an ISO or similar organization different to whoever owns and operates the generators because it fosters healthy competition between the generator companies, and that reduces the cost of electricity. It is worth reiterating that everything involved in the market clearing process is time variant. Supply curves, demand curves, quantities, and prices. Fluctuations and spikes occur in electricity prices when the demand and thus the supply fluctuate and spike. Frequent and large price changes are very characteristic of electricity markets and seldom observed elsewhere. I mean, when's the last time you saw espresso prices changing by a factor of 100 within a day? Another difference between the electricity market and other markets is that disconnect between end customers and market prices. When you purchase espresso or any other good, you are aware of the price at the time of purchase. However, residential and commercial grid users, and thus the utility companies through whom they purchase electricity, decide how much electricity to consume based on a crude approximation of the real-time price, such as fixed electricity rates that are higher during the day and lower at night. Such loads are described as inelastic because they are inflexible or unresponsive to the real-time price. Inelastic loads, also known as non-dispatchable loads, are modeled by a demand curve that is perfectly vertical and representative of a fixed quantity of power being bought at a given point in time. This lack of flexibility can make the price volatile, causing price spikes to occur when the demand is high, or when the supply of cheap electricity is intermittent, in the case of wind or solar. Industrial consumers avoid price spikes by becoming dispatchable loads, consuming only at or below a certain price. And similarly, utility companies use demand response programs to curtail things like EV charging or air conditioning at times when the demand and price would otherwise be excessively high. On the supply side, there are also dispatchable and non-dispatchable generators. We'll assume all loads and generators to be dispatchable, as that is the general case, and any non-dispatchable resource can simply be modeled as a dispatchable one. A caveat is that the non-dispatchable power quantities that are used when clearing the market are based on predicted generation, like wind and solar, and load, unlike the concrete quantities offered by a dispatchable generator. Loads and generators submit bids to buy power and offers to sell power, respectively. Each bid or offer includes a list of price quantity pairs. And in one of these pairs, the quantity is the maximum quantity of power that a generator is willing to sell, or that a load is willing to buy, at the corresponding price in the pair. The price is measured in dollars per megawatt hour, also known as the marginal cost of generating an additional megawatt hour of electricity. And the quantity is measured in megawatts. For an offer, the price must monotonically increase as the quantity increases. And for a bid, the price must monotonically decrease as the quantity increases. And if these sound similar to supply and demand curves, it's because they are. In an electricity market with one load and one generator, the load's price quantity pairs would define the electricity market's entire demand curve, and the generator's price quantity pairs would define the market's supply curve, also known as a dispatch curve. And the intersection between the supply and demand curves determines the quantity of power, Q star, that will be delivered at the market clearing price, P star, which maximizes welfare. Consider this example shown. The generator says they're willing to produce up to 6 megawatts at $2 per megawatt hour, or up to 9 megawatts at $7 per megawatt hour. Note that this does not mean that they're willing to produce the first 6 megawatts at $2 per megawatt hour, and only the remaining 3 for 7. The generator has one price, and it changes if a certain volume is surpassed, just like in the cafe analogy. And the same principle applies on the demand side. The load says they're willing to consume up to 4 megawatts at $8 per megawatt hour, or up to 8 megawatts at $5 per megawatt hour. These price quantity pairs form the two staircases, the supply and demand curves that are shown in the figure. And the market in this example clears at Q star equals 6 megawatts and P star of $5 per megawatt hour. I encourage you to pause the video and explore this example, whether with pen and paper or your favorite math software or programming language. Doing this is how I learned electricity markets and why I created this material, since there's no substitute for getting hands-on. Now, what if we have two generators, G1 and G2, and two loads, L1 and L2? Each generator and load has its own supply or demand curve, formed by its price quantity pairs, as shown. These are known as individual supply and demand curves, as they represent individual participants in the market. In clearing the market, you still want to maximize the welfare. My cat is eating my feet. The total seller cost C is the total of the areas under each generator's individual supply curve, up to the quantity produced by each generator. And on the other hand, the total buyer utility U is the total of the areas under each load's individual demand curve, up to the quantity consumed by each load. Maximizing the welfare is an optimization problem known as the economic dispatch problem. The problem is subject to the constraint that the total quantity sold, which is QG1 plus QG2, must equal the total quantity bought, QL1 plus QL2. And this constraint represents the conservation of power flow. The optimization problem can be simplified by splicing the generators and loads' individual supply and demand curves into an aggregated supply curve and an aggregated demand curve, respectively. The aggregated demand curve can be formed by sorting the price-quantity pairs from high to low, and the aggregated supply curve can be formed by sorting them from low to high. This is known as merit order. The optimization problem can then be solved by finding the intersection between the aggregated supply and demand curves. However, we will see that the optimization cannot always be solved by splicing the generators and loads' price-quantity pairs into one supply curve and one demand curve. This is just one of the many things we'll learn in the next video. Until next time, thank you for learning about the electricity markets with me, and learn more about this and other technical topics on my blog or by visiting me on LinkedIn. Thanks.